Today we're going to use Ampere's law to find the magnetic field produced by an infinitely long solenoid. So if we remember what a solenoid is, we can draw a cylinder, like so. And we'll say that it has radius r. And now a solenoid is produced by wrapping a wire around the cylinder, such that it's tightly wound. And then the end of the wire comes out like so, and this is a solenoid. So what we want to remember is that there are n loops of wire per unit length, and we'll say that the entire length of the cylinder is L, and we'll direct it such that the positive z hat direction is up along the axis of the cylinder, and we'll say that the current flowing is I, and it flows into the wire at the top, and then we'll wrap around the solenoid like so and come out at the bottom in that direction. So the next step is to figure out what is the direction of the magnetic field produced by this solenoid. So if we draw a few of these loops larger and out here so we can better analyze them, we'll draw 3 loops and we'll say that the current flows like so. And due to the right-hand rule, we know that for each of these loops we have the current flowing in my thumb direction and the magnetic field will curl around like so. So it will start and curl around the wire. And what this means is that at each point on this loop around, we'll have a contribution to the magnetic field. However, here, this contribution in this direction here will cancel out with this contribution in that direction there from this loop. So, like similarly, at this part here, we have this component canceling with that equal and opposite component. And what we end up with, it's kind of hard to see from this diagram, but what we end up with is that if we put our thumb in the direction of the loops wrapping around the solenoid, we only have a component of the magnetic field pointing upward in the positive z hat direction inside of the solenoid, and outside of the solenoid, the magnetic field will point downwards in the negative z hat direction. So inside our solenoid, we'll have the magnetic field pointing up, and outside the solenoid, the magnetic field points down. And again, this is because all of the components that wrap around in between each of these loops will end up canceling out. So now we'll use Ampere's law in its closed integral form to figure out what the magnetic field is outside of the solenoid. We'll start with Ampere's law, which says that the magnetic field dotted with the infinitesimal length vector is equal to mu naught times the enclosed current by an Amperian loop of our choice. So we'll start off by looking at the magnetic field completely outside of the solenoid. And we'll draw an Amperian loop such that both sides of the Amperian loop, both sides of the Amperian loop are outside of the solenoid. And we'll say that the first side is at distance A, and the second side is at distance B. And right away, we can look at the right-hand side of Ampere's law and see that the enclosed current would be the current passing through this Amperian loop based off of the solenoid, based off these wrapped wires around the cylinder. What that means is that I enclosed, because no current actually crosses the surface of the Amperian loop, is essentially just 0. So we can simplify this completely and say that B dot dl is equal to mu naught times I enclosed is equal to 0. And therefore the magnetic field outside of the solenoid is 0 everywhere. So now let me know that the magnetic field outside the solenoid is 0 everywhere. There is no magnetic field outside of the solenoid. Let's find out what it is inside. So we'll start by drawing our Amperian loop now, such that half of the loop is inside the solenoid, and the other half of the loop is outside of the solenoid. It's our amp loop. And we'll say that our direction of the loop is such that dl points up inside and dl points down outside in the negative z hat direction. So we'll start with the left-hand side of this equation, and we'll see that inside the solenoid, on this side of the Amperian loop, B dot dl will simplify to the magnitude of B times dl, because the two vectors are parallel inside of the solenoid. Outside of the solenoid, of course, there is no magnetic field, so there's no component there. On the top and the bottom, the magnetic field is perpendicular to the dl vector, so that also contributes no magnetic field to this integral. So we can simplify through this integral and say that the closed integral of b dot with dl is simply now the integral, because we're no longer talking about all four sides and the integral is no longer closed, of simply the magnitude of b dotted with dl. And this is considering only the component that's inside of the solenoid. And one step further, we can say that the magnetic field is constant in magnitude at every point along this Amperian loop inside the solenoid. And then this becomes the magnetic field, magnitude of B, integral of dl. And of course, if we say that the Amperian loop has length L, then this integral just becomes magnetic field times L. And what that means is that the left-hand side of this equation becomes the magnetic field with L is equal to mu naught times I enclosed. Now the enclosed current passing through this loop is given by however many loops actually cross this surface of the Amperian loop, which essentially is going to be mu naught times n loops per unit length, and the length is L of this Amperian loop, and of course each loop carries a current I. So the enclosed charge is the current I traveling along this wire, and on each loop, and there's n loops per unit length of the total length of L, so the entire enclosed current is simply I n L. And then we can go one step further, cancel the L's, and find out that the magnitude of the magnetic field inside the solenoid is going to be mu naught times n times the current I. And of course, it's going to move upwards in the positive z-hat direction as we said before. So we can say that the magnetic field B is equal to mu naught times n times I in the positive z-hat direction inside of the solenoid and 0 outside of the solenoid at all points.